Deep underground, sealed away in former salt mines and geologic vaults, sit hundreds of thousands of barrels of radioactive waste. Most of the world treats these spent nuclear fuel rods as dead, useless trash. We bury them, heavily shielded, under the assumption they will sit in the dark for tens of thousands of years. But the physics of that material tells a different story. When a typical nuclear plant throws out a fuel rod, 96 but unlocking that fuel requires a process that creates a byproduct far more dangerous than the waste it started with. To understand why a fuel rod stops working with so much juice left, we have to look inside the reactor core. Nuclear power relies on fission. A specific type of uranium absorbs a neutron, becomes unstable, and violently splits apart, generating intense heat. That split also shoots out extra neutrons. Those newly freed particles ricochet outward, slamming into neighboring uranium atoms, creating a self-sustaining chain reaction. But splitting an atom leaves behind microscopic debris. Over 3 to 5 years, these broken atomic fragments, called fission products, start to rapidly build up. Eventually, there is so much atomic clutter that it soaks up those flying neutrons. The debris literally suffocates the chain reaction. Once the reaction slows down, the rod is pulled from the reactor and declared spent, though the vast majority of the uranium hasn't been touched. Unlocking that trapped potential requires fighting physics with extreme, highly dangerous chemical engineering. That engineering happens here, the Orano recycling plant on the western tip of France. It is a sprawling industrial maze featuring 24,000 rooms. Arriving fuel radiates lethal radioactivity and temperatures around 300 degrees Celsius. Transporting it safely requires a steel cask weighing 110 tons. Unloaded by remote-controlled machinery, the rods are submerged under 4 meters of water. They will sit in these cooling pools for 5 to 7 years. This years-long submersion is only the prerequisite. The rods must cool down significantly before they can survive the next stage of the chemical maze. Once cooled, the spent rods are completely stripped of their metal cladding and dissolved in boiling nitric acid. A solvent is added to isolate the usable uranium and plutonium from the dead fission debris. This extraction yields a highly sensitive byproduct. By separating the elements, the plant produces purified plutonium, the exact material required to build a destructive nuclear weapon. The reality of this risk materialized in the 1970s. India successfully extracted plutonium from civilian fuel to test a nuclear device, a move that prompted the U.S. government to immediately abandon its own civilian recycling plants. Because of this threat, handling purified plutonium requires extreme operational security. France loads the material into specialized trucks and moves it across the country in secret, under heavy escort by the French military. For many nations, this calculation is a deal-breaker. The sheer logistical nightmare of securing weapons-grade material outweighs the benefit of squeezing a few extra years of electricity out of their waste. If a country is willing to take on that security risk, they take the separated plutonium and mix it with fresh uranium. This creates MOX fuel, which can then be fed right back into standard nuclear reactors. But the process is messy. The massive volume of solvents, chemicals, and industrial equipment used to break down the original rods inevitably becomes contaminated, generating a significant amount of secondary radioactive waste. And the dead fission products from the very first step still remain. Since they can't be recycled, they are subjected to extreme heat and permanently sealed inside solid glass, a process known as vitrification. Even with advanced chemistry, the waste doesn't vanish. Recycling simply concentrates the most dangerous byproducts down to a fraction of their original size, reducing the required storage space by a factor of 5, while extracting a second life of power. This requires building subterranean fortresses, maintaining fleets of remote-controlled robotics, and paying for constant military security. Contrast all of that infrastructure with the current global market. Fresh, virgin uranium is still relatively abundant in the Earth's crust, and digging it out of an open-pit mine is incredibly cheap to mine. France absorbs this massive financial penalty by design. Because their nuclear infrastructure and military are state-owned, the government treats the high cost of recycling as a strategic investment to guarantee its own independent energy sovereignty. Until raw uranium becomes prohibitively expensive or new lab technologies scale up, Most nations will keep looking at that 96% of unused energy and decide to bury it. Right now, the pure economics leave them no other choice.